discussed implicit enumeration. So by definition, actually implicit enumeration, it is an systematic approach, or you can say methodology, to find some of the possible solution of a problem set. Like we are given an algebraic form, maximization or minimization function, and then we find some of the candidate solutions using branch and bound method. Okay, but this explicitly, the implicit enumeration, it is used for the 0-1 problems, which are binary. It means that each variable can have like only two values. Either it is 0 and either it is 1. So it can attain only two values. Okay. Now in implicit enumeration, actually, we have two kind of variables: the fixed variables and the free variables. The fixed variables are at each node, like some of the variables that we fix the values of. Like for example, at node 1, I fix the value for x1 to be 0 and x1 to be 1 for two branches separately. So now x1 is a fixed variable. We will not, consider that in the, taking the next values. We will not change the value of x1. In all the next branches, we will exclude the value of x1 in that, and we will, we will have like four. For example, here we had in the example that we were solving, we had like five variables: x1, x2, x3, x4, and x5. So if at node 0 or node 1, I, fix the value of x1 to be 0 and x1 to be 1 in two branches, then in the next iteration, all the iterations, we will not, change the value of x1. It will be fixed. So x1 from that point, actually, it will be fixed, and all other variables will be, the free variables. It can attain any value, either 0 or 1. And then going to the next branch, if it give us some best completion or feasible solution, it will further divide into two branches at that point. And at that point, we will devise another variable, for example, x2, to have fixed value of 1 and 0. Then at that stage, we will have the x1 variable, which was already fixed, and x2 variable that is fixed now. We will have now two fixed variables, and the three other variables, they will remain free, and they can attain any value like 0 or 1. And then we will go to another branch, and so on, and we will try to fix at each node. We will try to fix the value of another variable. We will make the free variable lesser and the fixed variables to be more and more. And that is how we achieve the values of fixed variables from x1 to x5, and we get a proper integer solution for the binary problem. So now, for example, here at node 0, we say that x1 is equal to 1 and x1 is equal to 0 for branch 2 and branch 3 respectively. So now here at this point, at either 2 or 3, the value of x1 is fixed. Now at point 2 or 3, we have like four other variables that are not fixed. Now here we say that x2 is equal to 0 and x2 is equal to 1. So at node 4 and 5, we have two variables fixed. x1 is equal to 1 and x2 is equal to 1. x1 is equal to 1 and x2 is equal to 0. So we have two combination. x1, x2 is equal to 1, 1, and x1, x2 is equal to 1, 0. So that is how we proceed with the each step or each node. So we started an example of it, and I will just explain some of the steps that we did so that you have your, the memory is refreshed. So we had a problem that says maximize z is equal to minus 7x1, minus 3x2, minus 2x3, minus x4, and minus 2x5, subject to constraint A and constraint B. And we have like five variables over here, which are decision variables, and they belong to 0-1 class, which is binary variables. So at node 1, we know that all the variables are free. We haven't actually fixed any variable to have specific value. So all variables will be free and none of it is fixed. So at first, at node 1, the best solution, like when we do a decision, when we make a decision, for example, buying a car or setting a factory or even buying some clothes in a market, in a supermarket. When we enter, we have two decisions, to be we that we can take, either buy or do nothing and leave alone without buying anything. So here at node 1, what we do is we do the best completion, and the best completion is to do nothing. Like we have 5 variables, so we insert the value of each variable to be 0, and we see that if this solution for which all decision variables are 0, you know they are they yield a feasible solution over here or not. And we know that the feasible solution is that for which it satisfies all the constraints. So it has two constraints over here. So we will put the values in each of the constraint, and we will say that you see that if it satisfy the constraints A and B or not. Okay. So for the first one, we say that we put the value of x1, x2, x3, x4, and x5 equal to 0. So we get in constraint A, we get minus 4 into 0, minus 2 into 0, plus 0, minus 2 into 0, minus 0. It's less than or equal to minus 3. So we get 0 on the left hand side and minus 3 at the right hand side, which is already fixed. And we say that 0 is less than or equal to minus 3, which is not true. So this solution actually, it is not feasible. It means that we have to make some changes in this. This is not feasible at all. Okay, because it is not satisfying the first constraint, and it is not satisfying also the second constraint. So the solution is not feasible. So at this point, actually, when we do not get any feasible solution for the best completion, we actually make branches, and we fix one variable and we look for other variable. We put the other variable equal to 0, and we see that if that is feasible or not. Okay, and here is the feasibility table. Okay, you need to either actually you need to have memorize it either, or you can just say that if the constraint is less than or equal to and the coefficient of the variable is negative, it means that the infeasibility, it will have a value of 1. But if the constraint is less than or equal to and the variable coefficient is plus or positive, it means that it will have a value of 0. Similarly, if the constraint is greater than or equal to, yes, this is the coefficient variable. Here it is minus 4x1, so minus 4 is the coefficient variable, coefficient of the variable x1. Minus 2 is the coefficient of our variable. Yes, what is the value of x1 in each constraint? Here it is minus 4, and the constraint is less than or equal to. So minus refers to that x1 we will take as 1. Minus 2 here we will take it as 1. It is plus positive for x3. We can say that here it is 1 actually. Whether we write it or not, it is 1. No, you have to take all the variables actually, depending on which node you are. Like right now we are at node 0. It means that all the variables are free. So we will go for all the variables values. But at node 2 or 3, actually, when x1 is fixed, So we will, ignore x1, and then we will go for x2, x3, x4, and x5. At node 5 and 6, we will ignore the x1 and x2 because we know that x1 and x2 values will be fixed. So we take x2, x3, and x4. At node 5 and 7, maybe we say that three variables are fixed. So we will take the value of x4 and x5 only. So that is how we proceed with each node. Do you understand it now? Okay. So first of all, at node 1, we need to do is we do the best completion, and the best completion is to do nothing actually. And how to do nothing? It means that all the variables will have a value of 0. So here we put all the values of x1, x2, x3, x4, and x5 equal to 0. And we see that whether these values satisfy constraint A or B or not. So when we put the value, it says that 0 is less than or equal to -3, which is not true actually. 0 is greater than -3. So it does not satisfy the constraint A. Similarly, when we put all the values equal to 0 in the constraint B actually, we get 0 is less than or equal to -7, which means that it is also not true. Okay, so this means that this solution, that x1 is equal to x2 is equal to x3, x4, and x5, the solution is not feasible. So whenever we get non-feasible solution, what we do actually is that we branch it out and we fix an arbitrary variable. For example, if we have like 5 variables, so we can fix any of the variable x1, x2, or x3, or x4, or x5, any of it. But we will go in sequential form. So a sequential form is kind of, you have like a sequence in it. So we will get the x1 value to be fixed. So x1 can actually add these are all binary variables. So it can attain only two values. Either it will be 1 or it will be 0. So here we have two branches actually. These are okay. Okay, so just to let you know, you need to do, use this table for feasibility. Okay. Now, when we fix the value of x1 is equal to 1 and x1 is equal to 0 over here, we have node 2 and okay. Okay. So now when we fix we did up till this point where we have like x2 and x1 fixed. Okay. So now using the last in and first serve LIFO method, we will analyze the node 5. For the node 5, we say that x1 is equal to 1 and x2 is equal to 0. These two are fixed. Okay. And the free variables are x3, x4, and x5. So here we will do the best completion. Okay. Now for the best completion, actually, I will start it from here. Okay. Now we are at the point where we left. Okay. So here we put x3, x4, and 5 is equal to 0, and x1 is equal to 1, and x2 is equal to 0 in A and B. So for A, we get -4 into 1 minus 2 into 0 plus 0. Mm, this is the constraint A. Okay. So -4 is less than or equal to -3, which is true. For B, we will have -4 into 1 minus 2 into 0 -0 plus 0 plus 0 less than or equal to -7. -6 is less than or equal to -7, which is not true. So it is yielding a non-feasible solution. We can say that it yields non-feasible solution. So what we do when we have a like non-feasible solution? Any guesses? Yes. So we will branch it out. So we will branch actually here we have like 4 and 5 and 5 will be branched to 6 and 7. So here we had like x1 is equal to 1, 1 is equal to 0, x2 is equal to 1, 2 is equal to 0. And here we will have x3 is equal to 1 and 3 is equal to 0. Okay. Now what we will do is we fix x3. Okay. And already we have x1 is equal to 1, x2 is equal to 0 fixed. Okay. Now we will do it for the node 6. Okay. So now for the node 6 we have actually fixed is equal to x1, x2 and x3, and free are x4 and x5 only. Now we know that for the values for x1, x2 and x3 for node 6 are, this is the node 6. So we have at node 6 x1 is equal to 1, x2 is equal to 0 and x3 is equal to 1. So 1, 2 and 1 are the values that we will look for. So now x1 is equal to 1, x2 is equal to 0 and x3 is also is equal to for node 6 it will be 1. So x4 we put 0 and x5 we put 0 for best completion. Okay. Now putting the values in A and B, we get as minus 4 into 1 minus 2 into 0 plus 1 minus 2 into 0 minus 0 less than or equal to minus 3, which gives us minus 4 minus 4 into 1. So minus 8 is less than or equal to, sorry, plus 1. This is plus 1. Minus 4 plus 1, it will give us minus 3 less than or equal to minus 3, which is true. And for B, it will give us minus 4 into 1 minus 2 into 0 minus 4 into 1 plus 0 plus 2 into 0 less than or equal to minus 7. Here we get minus 8 less than or equal to minus 7, which is also true. So now it is giving us a feasible solution. So what will we do when it gives us a feasible solution? It means that node 6 is candidate solution. It can be potential solution. But we still have to explore x7, the seventh node, the third node and the fourth node. So we will explore all this and then we will compare the result with this one. So here at node 6, actually at node 6, x1 is 1, x2 is equal to 0, x3 is 1, x4 is equal to 0 and x5 is equal to 0. And the value for z is equal to What will be the value for z? The value for z will be -7 into 1 minus 3 into 0 minus 2 into 1 minus 0 minus 2 into 0. It will give us -7 minus 0 minus 2 minus 0 minus 0 minus 9. Z is equal to -9. So now this is one of the bound, okay? It is a candidate solution. Now we will find the solution for all other nodes and we will compare it with the z is equal to 9 -9, and we will see if it is greater than or equal to this one, and then we will have like a final output. We can compare the solutions and we can say that okay, this one is the final solution for the problem. Okay, now the next node that we have to analyze is node 7. Okay, so for node 7 we also have the fixed variable is equal to x1, x2 and x3, and free are x4 and x5 only. Now x1, x2, x3 are fixed, so x1 is equal to 1, x2 is equal to 0, and x3 is equal to 0 over here. Now for best completion, actually, we put x4 is equal to 0 and x5 is equal to 0. So putting all these values in A and B. So for A, we have -4 into 1. Okay. And -2 into 0. It will also be 0, 0 and 0 less than or equal to -3. So -4 is less than or equal to -3, which holds true actually. And for B, it will be -4 into 1, -2 into 0, -4 into 0, plus 0, plus 2 into 0, less than or equal to -7. It will give us -6 less than or equal to -7, which is not true actually. Okay. Now, if it is not true, we will actually check for the feasibility using table. Okay. Now, checking for feasibility, what will be the possible feasibility? Okay. Now we have x1 is equal to 1, x2 is equal to 0, and x3 is equal to 0, okay, which are fixed actually. We can only, change the value of x4 and x5. Okay. So we put both the values as x4 is equal to 1 and x5 is equal to 1 over here, and we will see whether it satisfies it or not. So here we get -4 into 1 minus 2 into 0 plus 0 minus 2 into 1 minus 1 less than or equal to -3. So it will give us -4 minus 2 minus 6 minus 7, which is true. And for B, what we get is -4 into 1 minus 2 into 0 minus 4 into 0 plus 1 plus 2 into 1 less than or equal to -7. So it will give us -4 plus 1 minus 3 plus 2 minus 1 less than or equal to -7, which is not true. Okay. Now putting it will be not branched further. it will not branch actually, because it is not even given the best completion and it is not giving us the feasibility. So it will be not branch further. Now what we do is we analyze node 4 which was left, and then node 3 it was also left. So we just analyze node 3 and node 4 and we will see if that solution help us. Okay, so now at node 4 actually we have two variable fixed, x1 is equal to 1 and x2 is equal to 1. Okay, so now x1 is equal to 1 and x2 is equal to 1, that are fixed, and for best completion x3, x4 and x5 these are unknown. So for best completion, okay, we put x3 is equal to x4 is equal to x5 and all of them are put equal to 0. So what we get is in constraint A we get minus 4 into 1 minus 2 into 1 plus 0 minus 2 into 0 minus 0 less than or equal to minus 3, which is actually true. Minus 4 and minus 2 minus 6 is less than minus 3, so it is true. For B, minus 4 into 1 minus 2 into 1 minus 4 into 0 plus 0 plus 0 less than or equal to minus 7. So minus 6 is less than or equal to minus 7, which is not true. It is giving us a non-feasible solution. Okay, now we check the feasibility using table for node 4. So x1 is equal to 1 and x2 is equal to 1, these are fixed. Okay, now here we put x3 is equal to x3 here is it will be equal to 0. X4, as the coefficient is minus 2, so it will be 1, and x5 the coefficient is minus 1, so it will also be 1. Okay, so putting in A we get minus 4 into 1 minus 2 into 1 plus 0 minus 2 into 1 minus 1 less than or equal to minus 3. It gives us minus 6 minus 8 minus 9 less than or equal to minus 3, which is true. Now for B actually we have x1 is equal to 1 and x2 is also is equal to 1. For the third variable, the coefficient is minus 4, and we know that for negative coefficient we will have a value of 1, and x4 is positive, so it will have a value of 0, and x5 is also positive, so x5 will be equal to 0. Now putting these values in equation B, we get minus 4 into 1 minus 2 into 1 minus 4 into 1 plus 0 plus 0 less than or equal to minus 7. So it will give us minus 10 less than or equal to minus 7, which is also true. So it is giving us feasible solution. Okay. Now the best solution that we can get over here is z is equal to minus 10, which is less than minus 9, and it is maximization function, so we reject this solution. Okay. Now the only node left is node 3. Okay. Now I will check whether node 3 gives us some solution or not. So for node 3, when we see over here is only one is fixed, x1 is equal to 0. Okay. So x1 is equal to 0, x4, x3, x2, and x5. These are unknown. Okay. Now put all x2 is equal to x3 is equal to x4 is equal to x5 is equal to 0 and put in a, we get is minus 4 into 0. It will give us 0 actually less than or equal to minus 3, which is not true. It is not giving us feasible solution. Okay. And hence the only solution, two solution that we get is 8 not 4, which is minus 10, and 8 not 7, which is actually sorry, 8 not 6, which is minus 9. So minus 9 is better than minus 10. So not 7 is the not 6 is the best solution that we get. And for that, x1 is equal to, we see that at not 6 actually, we get x1 is equal to 1, x2 is equal to 0, x3 is equal to 1. Okay. x4 is equal to 0 and x5 is equal to 0. So x1 is equal to 1, x2 is equal to 0, x3 is also is equal to 1, x4 is equal to 0, and x5 is equal to 0, and z is equal to minus 9. So this is the best possible solution that we get for this question. I hope you have, understand the whole process of it, because I skipped some of the, procedure because it was repeating, and you told me that, you already know these things. Yeah, so this is how the implicit enumeration is actually done. And it is simple, but it is, a bit lengthy process. So in the exam, it may be given like, you have like given only three variables maybe, okay? So it will be like just an iteration one or two up till two iteration, because in the first iteration we will fix like x1, okay? And x2, x3 will remain, the free variables. And in the next iteration, we will fix either x2 or x3, and only one will be free variable, and that is you can deal with it in only two iterations. So in exam, it may be like, the teacher may approach you for only a problem with only single variable in a, sorry, single variable, single iteration or two iteration. At least, at most, it will be have like two iteration. Yes. Yes, yes. We will, today we will, start the cutting plan method. Yes. So next topic that we will be doing is the cutting plan method. I hope you have like, the teacher has already done some of the questions on cutting plan method. Now I will do, first I will introduce the topic, and then I will be doing the, problem R2 on cutting plan method, because that is a little bit, complex than implicit enumeration. That is a bit technical. So you need to know a few things. Okay, I will have some papers, and then we can actually start the next topic. Okay, I will get some paper from my cupboard, and we can start it. Yes, yes, yes. the splitting of it. Yeah, it is a kind of procedure that we do in the cutting plan method. So let me just introduce the basic procedure of the cutting plan method. So just like we do the branch and bounding, do you remember the branch and bounding? We had like relaxed LP solution. And by relaxing, I mean that we ignore integer constraint from the problem. Okay. Then we solve it using simplex. Okay. Then we devise the Gomri's cuts actually to incorporate actually the integer constraint of it. Okay. And finally, using dual simplex, we get final integer solution. Okay, so these are the four actual basic steps of the cutting plan method. Okay, the first thing is that we use simplex. Okay, and the first of all, we actually ignore the integer constraint of the problem. We solve it using simplex or any other method to get the basic solution of it. When we get the basic solution of it, it will be in some decimals or in fractions actually. Then we get the okay. So today in this session we are going to do the cutting plan method or cutting plan algorithm. Now the first basic thing in this is to remove integer constraint from problem. And then when we remove the integer constraint, we solve it using simplex. We know that in simplex we get you know fractional right hand sides. Sometimes we do not get integers. Okay, so if we get integers, we don't need to do the cutting plan method. But if we get the fractional right hand side, then we proceed to the geometry cut. Okay, for this, the first step is to choose any constraint whose right hand side is in fractional form, or we can say it in decimal form. Okay, the step two is to changing right hand side and constraint into x plus f form, where f is fraction and it is somewhere between 0 and 1. Okay, then in step 3 actually what we do is we separate x's from f's. That is, we put x's on left hand side and equate it to the fractions on right hand side. Then in step 4, what we do is we put fractional right hand side less than or equal to 0. After this, now this is the Gomri's cut actually. This thing is the Gomri's cut. Now after this, by putting it into less than or equal to 0, it means that it is ready to be processed, because here we will put the slack variable. So we add another slack variable or change it into standard form, and put it in final table. When we put it in the final table, the step number 6 is to solve it using the dual simplex method. Okay. In dual simplex method, the step 6i is that the negative right hand side is the pivot row. In the 7i, we need to find is the entering variable using dual ratios. Okay, and the 8i is to find integer solution. If the solution is integer on this stage, we close it, we do not move it further. But if it is still not integer and one of the right hand side is still in negative form, we repeat the procedure from step 1 to step 7i again and do it again until we get the integer solution for it. I will now go towards an example. I will solve it and you will I will explain every step of it so that you know the whole procedure of it. Okay, so we have a problem which is maximize z is equal to 8x1 plus 5x2 subject to x1 plus x2 less than or equal to 6 and 9x1 plus 5x2 is less than or equal to 45 and x1 x2 belongs to z and are greater than or equal to 0. So it are non-negative and also x1 x2 are integers. Now the first thing is to remove this thing. We will remove or we will relax ILP into LP problem. Okay, so we will write it at x1 plus 5x2 subject to x1 plus x2 less than or equal to 6 and 9x1 5x2 less than or equal to 45 and x1 x2 greater than or equal to 0. So it will be the next form of this problem. Okay. Now changing it into the standard form. It will be z minus 8x1 minus 5x2 plus 0s1 plus 0s2 equal to 0 and subject to, you know, the whole procedure of simplex. Okay. So it will be easy for you. Okay, so multiply it with minus 1. Yes, exactly. Yes. So now I will make the table of it. So this is the basic variable. Here we have z, and we have s1 and s2 as over here. Here we will have x1, x2, s1, s2, right hand side. Okay. Here in z we have minus 8, minus 5, 0, 0, and it is 0. S1 is equal to here 1, 1, 1, 0, 0, 1, and it is 9 and 5. The right hand side is 6 and 45. Okay. So now here it is maximization function. So x1 is the most negative one. So x1 is the entry variable. Okay. And I will skip some of the steps, just to, keep it, in some faster pace. Okay. So this is the pivot column. Okay. So 6 over 1 and 45 over 9. So it will become 6 and it will become 9, 5, the 45. 5. Now it is the minimum positive. So S2 will leave the system and X1 will enter the system. Now this is the pivot row and this is the key element. So key element is equal to 9. So new pivot row is equal to 9, 5, 0, 1, 45 divided by 9. That we will get 5 by 9, 0, 1 by 9 and 5. So this is the new pivot row, or we can call it, because X1 will enter here, so it will be X1 row. You understand this point? I term the new pivot row as X1 row because X1 will enter over here instead of S2 and S2 will leave the system. Now the new Z is equal to old Z minus pivot column coefficient into new pivot row. It will be equal to minus 8 minus 5, 0, 0, 0, minus 8 into 1, 5 by 9, 0, 1 by 9 and 5. So minus 8 plus 8 will be 0 and minus 5 and plus 40 by 9. Minus 5 plus 40 by 9. So plus 40 by 9 will give us, it will give us minus 0.55. Okay, and 0 plus 8 into 0, it will be 0, 0 plus 8 into 8 by 9 is equal to 8 by 9, and 0 plus 8 into 5 are 40. It will become this one. Okay, so this is the new Z. Now we have a new S1 row to be found. It will be equal to old, which is 1, 1. I'm just writing it, now 0, 6 minus 1 into 1, 5 by 9, 0, 1 by 9, and 5. So we will get over here is 1 minus 1, 0, 1 minus 5 by 9 minus 5 by 9. Sorry, 1 minus 5 by 9. Will be equal to 0.44, and 1 minus 0 is equal to 1. And yes, closed. Can you see? Okay. So 0 minus 1 by 9 is minus 1 by 9, and 6 minus 5 is equal to 1. So this is new S1 row. Okay, now we will update the table. Updating the table, we get basic variables. Here we have Z, here we have S1, and instead of X2, we will have X1, 2, S1, S2. We can apply it to any of the method, but you need to remove the integer constraint, because in two phase or in M method in simplex we do not count it for the integers. We do it for the continuous variables, because we get decimals over here. In fractions, we get answers in fractions actually. So simplex is, yes, most of the time simplex, because it is quite easy to to do it. You just have to multiply. If you have greater than or equal to, you can convert it to less than or equal to, and if you have like minimization function, you can convert it into maximization by multiplying it by -1. you know yes. So when we have fractions or in decimals, it means that they are not integers. Like for example, we have z is equal to 0.5, so that is not an integer. That is decimal or in fraction. In fraction, it can be termed as 1 by 2, or in decimal it is 0.5. So that is the difference actually. In integer, yes. So in integers we have like 0, 1, 2, and this kind of form of numbers. Okay, now for z we have 0 minus 0.55, 0, 8 over 9, and 40. For S1 we have 0, 0.44, 1 minus 1 over 9, and 1. For X1 or the new pivot row, it is 1, 5 by 9, 0, 1 over 9, and 5. Now here we have X2 as the negative one. So X2 is the entering variable, and the leaving variable is 1 over 0.44 and 5 divided by 5 by 9. So here we will get here 2.27 over here, and here we will get 45 divided by 9. 9. So this is the minimum positive. Okay. So S1 is the leaving variable. Now the new pivot row. This is the pivot row. This is the pivot column, and 0.44 is the key element. So it is 0, 0.44, 1 minus 1 over 9, 1 divided by 0.44. So here we get 0, 1, 1 by 0.44. It will give us 2.27, and minus 1 divided by 9, it will give us minus 0.11, and 1 divided by 1.44, it will give us again 2.27. So this is the new pivot row. Now new z is equal to 0 minus 0.550 8 over 9 40 minus 0.55 into 0 1 2.27 minus 0.11 and 2.27. Do you understand why I wrote all these things? These ones. This is the old z minus pivot. This is, yes. So I just, want to know the basics of it, and just repeat it with me. Plus 0.55 into 2.27, it will give us 0.55 multiplied by 2.27. 1.24 and 0 plus 1.24 is 1.248, 1.25. Okay, and 8 by 9 minus 0.55 multiplied by minus 0.11 will give us minus 0. 0.82 and 40 minus 0.55 multiplied by 2.27. 1.24, so 40 plus 1.28 will give us 1.25. So it will be the new z. Okay, now new x1 is equal to the old x1, which is 1, 5 by 9, 0, 1 by 9, and 5 minus 5 by 9 into 0, 1, 2.27 minus 0.11 and 2.27. So it will give us 1 minus 5 divided by 9, 0.44. 5 by 9 minus 5 by 9 is 0. 0 minus 5 by 9 into 2.27. So 5 divided by 9 multiplied by 2.27 is equal to minus 1.26. Now 1 by 9 minus 5 divided by 9 multiplied by minus 0.11 will give us 0.172, and 5 minus 5 by 9 to 2.27. Give us 3.75. This is the new x1 row. Okay. Now updating the table, we get z x1, x2 and x1 and x1, x2, s1, 2 and right hand side. So for z, the new z is equal to 0, 0, 1.25, 0.82 and 41.25. Okay. x2 here, which is a new pivot, is equal to 0, 1, 2.27 minus 0.11 and 2.25. Now here it is equal to 0.440 minus 1.26, 0.172, and this is 3.75. Now we see that all the right hand sides are in fraction actually. So z is equal to 41.25, which is in fraction or decimal. Okay, x1 is equal to 3. Yes, these are all positives now, and this is maximization function. So it means that the optimal solution has arrived. So this is the optimal. Yes, it is maximization. Yes, and so it doesn't matter. It is still no. If the right hand side is negative or positive or zero, you don't have to perform any iteration unless and until you have here a negative one in this one in the z row, not on the right hand side but on the left hand side. Yes. So that is the indication of it that the optimal solution has arrived because these are all positive. It will either zero or positive. If it had negative, like for example, if it had negative over here or here, then we will again do another iteration, and that would be the entering variable actually. Okay. Yeah. So now we see that the right hand sides are in fraction. Okay. And in the cutting plan method, we say that choose any constant whose right hand side is in fractional form. Okay. If it were integers, we do not have to do any cut and playing method or branch and mount or any other method. Okay. That was okay for us. But it is in fraction. So we have to do is a cutting plan method. We have now to start the cutting plan method. Okay. Now we have you know, two right hand sides for two variable for x1 and as well x2, which are in the fractional form or in decimal form. One is 3.75 and one is 2.25. So what we do is we select the constraint which has the right hand side, equivalent to or nearer to 1 by 2 or 0.5. Now we see 2.25, it is nearer to 0.5 by 0.25. And if we see here, it is 3.75. So it is also like near to 0.5 by 0.25. So we can, as the difference is both like, 1 over 2, we can choose arbitrarily anyone. Okay. So you didn't understand that. Okay. Okay. Now here we see it is 2.25. Okay. If it were 2.5 and it were 3.75, which one was nearer to 2.5? This one was nearer to 0.5. We can write it as 2 plus 0.5. Okay. And we can write it as 3.3 plus 0.75. Okay. So this is the fraction part of it. It is nearer to 0.5 or 1 over 2 more than this one. Then we would have selected the x2 constraint, this one constraint. But in this scenario that we had over here, we had 2.25 and 3.75. So 2.25 is equal to 2 plus 0.25. Now, and 3.75 is equal to 3 plus 0.75. Now, if you want to convert this into 0.5, we have to add 0.25. Okay. And if we have to make this 0.5, we have to subtract 0.25. So both are at the same length from 0.5. So we can choose either x1 or x2 arbitrarily. Yes, yes, I can give you. Yes, yes. For example, uh, we have a problem. I will come to another solution, another problem. I will do it on the cutting plan method. I hope that it has like some values that we can explore. Okay. Okay. For example, I make a table here in which we have x1, x2, s1, s2, and the right hand side over here. Okay. Now it is 0, 0, minus 4 by 5, minus 18 by 5, and 88 by 5. And the second one is 1, 0, minus 2 by 5, 1 over 5, and 4 by 5. The second constraint is 0, 1, 1 over 5, minus 3 by 5, and 8 by 5. Now here, if you want to select, this is 4 by 5, okay? So 4 by 5, it means that it is somewhere, like if you convert into decimals, it will be 0.5, okay? Now, here it is 8 divided by 5, which is, it is 1.6, which is equal to 1 plus 0.6. Now, which one is more, nearer to 2.5? This one. It is 0.5. It is 0.6. You see? Here we will, select, for example, this is x1, this is x2. We will select x1. You got it now? No, because this is the part of the algorithm that it says that the value nearer to 0.5, you have to select that constraint, which has the decimal value, nearer to 0.5. You have to select that one, that near to 0.5. Yes, that is selected. Now it is not nearer to 0.5. What? This is 1.6. Yes, yes, this is allow. Yeah, this is a rule in this algorithm. You can say that. This is not 0.5, 0.8. Okay. Yes, yes. 0.8 is equal to 0 plus 0.8. We can write it as. And here we can write it 1 plus 0.6. So this one is nearer. Yes, 8 by 5 is nearer. So we will select the x2. Yes. It was. Yes, I can give you one last example. Okay, let me make another table. We have x1, x2, s1, s2, and right hand. Okay, here we have. Okay, I will ignore the first one. I will just say it is 5 by 4 and this is 5 by 2. Okay, so 5 by 4, we can write it as, what is the value? 1.25. Okay, and 5 by 2, it is equal to 2.5. So this one is more nearer. It needs 0.25 to reach 0.5 and it is already 1.5. So 2.5 is nearer. So we need to select this one, this row, this constraint. Yeah, so that is how it is actually, done in the cutting plan method. Okay, so now in this procedure, we see that changing the right hand side and constraint into x plus f form. Okay, well, f is the fractional form of it. Okay, now we take that constraint. Now here it is 2.25, it is 3.75. Okay, both are 0.25 nearer to 0.5, so we can select arbitrarily. We choose x1, for example. Okay, now x1 over here actually is, let me explain it a bit. Okay, now here we have the x1 here is equal to this should be equal to 1, not 0.44 actually. This will be equal to 1. Okay, now we have the s1 over here is x1 plus 0x2. Just write this constraint. Okay, minus 1.25 x s1 minus 0.25 into s2. This is 0.25. It is not 1.82. I have messed some calculation, made some miscalculation over here. Okay, I will just make the table again, and I can just explain this term to you. Okay, this is the final table from the book, which says that it is 1, 2, s1, s2, and right hand side 0, 0, 1.25. Yes, we are. I am continuing it. I'm not doing anything else. I'm just rewriting the table. Yes. Okay, now these both are, the we select x1. So the x1, this constraint can be changed into, here the coefficient of x1 is 1, so we can write it as x1. Here the coefficient of x2 is 0, so we can write it 0x2. Here the coefficient of s1 is minus 1.25, so we can write it 1.25 s1. Here the coefficient of s2 is 0.25, so we can write plus 0.25 s2, okay, equal to 3.75. Okay, now the thing is to change is to x plus f form, where f is the fraction and f is actually greater than or equal to 0 and less than or equal to 1, between 0 and 1. Okay, so now here we have x1. Now 1.25 minus 1.25, we can write it as minus 2 s1 plus 0.75 s1. We can write it as, it will give us exact minus 1.25 s1. Do you understand the step? Hello? Zero 0.75 actually. If we subtract, actually, we have 2 s1 minus 0.75 s1. Okay, minus 2 plus. Okay, so if we add 0.75 to 2 minus 2, what will we get? minus 1.25 as 1. So we exact the same value here over here. We can write it in this form. You need to convert these fractions actually into integer and fractional form. So minus 1.25, it can be written as minus 2 plus 0.75 into S1. Look, just like we can write 0.25, okay, we can write it as minus 1 minus 0.75. Can we write it as 1 minus 0.75? Similarly, I wrote minus 1.25 as, yes, they are equal. 1, 1 over 3, 0, and 2. Okay. Similarly, we will find new Z and we will find new S2 row. Do you understand this step? Okay. And it will be equal to alt Z minus pivot column coefficient, the new pivot row. Okay. And this will be equal to alt S2 minus pivot column coefficient into new pivot row. And new pivot row is this one. Okay. So now doing the same procedure, okay, we will go to the final table of it. Okay, we get the, after doing 2 iterations, we get the final table as, should I do the iterations or should I skip it? Okay. So here, what we get is, yes, from Torah and also, uh, so in some questions, like in exam, maybe you will be given the first. Okay, now do the cutting plan method. Apply the cutting plan method. It actually final table. Yes, yes. You will be asked in exam final table, and you will be asked like do this cutting plan method to find the integer solution for it. Let me write the final table over here. From here we will start. Now we see that this one, the right hand side for x2 as well as x1 is in fraction form. So 7 by 2 is equal to 3 by 5, 3.5, and 9 by 2 is equal to 4.5. We will convert all these. 56 by 11 is equal to 56 by 11 is equal to 5.09 are equivalent to 5.1, and 30 by 11 is equal to 2.727, and 7 by 22 is equal to 0.318, and 1 by 22 is equal to 0.045. Okay, so I'm writing all these fractions and converting into decimal. Only one left, which is 3 by 22. So 3 by 22 will be equal to 0.136. Okay, now making another table with the decimal values. Okay, now 5 by 6, 56 by 11 is equal to 5.09. Okay, 30 by 11 is equal to 2.72, and 8 is equal to 126. X2, it is equal to 0, 1. 7 by 22 is 0.318, and 1 by 22 is 0.045, and right hand side is 3.5. X1 is equal to 1, 0, minus 1 by 22 is equal to minus 0.045, and 3 by 22 is 0.136 equal to 4.5. Now we can pick either x1 or x2, you know, because both are 3 plus 0.5 and 4 plus 0.5. So both are to nearer to 0.5 at the same distance. Both are at the final spot at 0.5. So we can either pick x1 or x2, you know. Now we pick x2 arbitrarily. Okay. Now getting this one into the algebraic form. So we get 0x1 plus 1x2 plus 0.318 can be written as 0.32 s1 plus 0.045 can be written as 0.04 s. This one negative 3.5. Yes, it is possible that it has negative value, but only z value will be negative. The x1 and x2 will be positive, but will be in fraction form. And it will be like when we have like a minimization problem or something like that. But it is possible that it has a negative value. It is quite possible. But x1 and x2 will have a positive value because we know that we write x1, x2 greater than or equal to 0. So it cannot be negative. It is non-negative constant, and we add it to every question. So x1 and x2, the right hand side, it cannot be equal to a negative value. Z can be equal to a negative value, but x1 or x2 or x3, the decision variables, they will not be equal to some negative value. that will not be equal to less than 0, because we add x1, x2 or x3 greater than or equal to 0 as a constraint which is non-negative constraint. It is mandatory for all the problems. Okay, so now I am writing this constraint into the algebraic form. Here for the coefficient for x1 is 0, so I am writing 0x1. Here the coefficient of x2 is 1, so I am writing 1x2. Here for S1 the coefficient is 0.318, so I am taking it at 0.32. I am rounding it off, S1, and 0.04 S2 is equal to 3.5. Now this is the complete algebraic form. Okay, now we will derive the Gomez cut from it. Yes, it is from the book Operation Research. I will send you the book if you want me to send it, or either I will send you a screenshot of the problems. Let me send you the screen. Okay, I will send you the screenshot of the problem. Okay, just a second. Okay, I'm sending you from my laptop. Okay, I just sent you the problems. Okay, and this is the, yeah, this is the group A, the one, the first one. Yes, yes, you can practice it. Okay, so similarly, I will send you for the implicit enumeration, and also I will send you for the branch and bound. Okay, so here now I will derive the Gomez cut from it. Now, how to derive Gomez cut? Do you know the procedure of it? To derive the Gomez cut, actually, we will write all the variables which has fraction in it into x plus f form. Okay, where x is the integer part and f is the fractional part. Okay, and 0, the fractional part is between 0 and 1. Okay, now 1x2, it can be written as 1 plus 0x2. Okay, so you don't need to write the fractional part of it. Okay, for 0.32 s1, it can be written as 1 minus 0.68 into s1. Okay, and the 0.04 s2, it can be written as 1 minus 0.96 s2. We can write it, and 3.5, it can be written as 3 plus 0.5. Now writing all these values into this one. So we will get it as x2 plus 1s1 minus 0.68 s1 plus 1s2 minus 0.96 s2 is equal to 3 plus 0.5. Okay, now what we will do is we will collect all the variables which has integer part on one side and all those who have fractional part on the other side. So we can write it as x2 plus 1s1 plus 1s2 minus 3 is equal to, this 3 will, it will transfer to this side, and all these it will be transferred to which has the actually the fractional part, it will be transferred to another side. So it will become 0.6 at S1 plus 0.96 S2 plus 0.5. Okay, so that is how. Now we will write this one as, we will ignore this one. This part is ignored. We are only interested in the fractional part of it. So we can write it as 0.6 at S1 plus 0.96 S2 plus 0.5 is less than or equal to 0. So this is actually the Gomez cut that we will introduce into the final W. Now, for that, we need to write it, less than or equal to some right-hand side value. So the 0.5 here, it will move to this side, and let's see what happens. So it is 0.6 at S1 plus 0.96 S2 is less than or equal to minus 0.5. Okay, now it is the complete cut. Okay, now it is less than or equal to, so whenever there is less than or equal to, we introduce slack variable. And it will be S3 because we already have S1 and S2 over here. So we will introduce S3. It will become 0.6 at S1. Yes. Okay. From this, actually, from this W, the final W, we got the variable that we are going to investigate. Okay. Now, this is, and that depends upon the right hand side value of the that variable. Now for x2, this is 3.5, and for x1 it is 4.5. So both are equivalent actually in the fractional part. The fractional part of both is 0.5. This can be written as 3 plus 0.5. This can be written as, yes, yes, the fractional. Yes, we will, because the integer is fixed. Integer is fixed. It will get us some value, like it will be either 4 or 3. So we need to investigate the fractional part of it. Okay. Now we can pick either x1 or x2. So I pick x2 over here. We can also pick x1. That's not a problem. Okay. And we will write this one, this whole constraint actually into the variable, the variable form, the algebraic form. Here the coefficient of x1 is 0. So I wrote 0x1 plus 1x2 plus 0.32 S1 plus 0.04 S2 equal to 3.5. Okay. Now we will write the parts which has, which has the fractional, which are in the decimal form. We write it as a x plus f form, where f is the fractional part and x the integer part. So 0 is already integer, so we do not need to change it. 1 is also already integer, we do not need to change it. The only three things that we need to change is this one, and the right hand side, which is 3.5. Now 0.3 to S1, it can be written as 1 minus 0.68 into S1, or 1 S1 minus 0.68 S1. It will give us exactly 0.32 S1. Okay. The 0.04 S2, it can be written as 1 minus 0.96 S2. Okay. It will give us exactly 0.04 S2. And 3.5, it can be written as 3 plus 0.5. It will give us 3.5 back. Now we are writing this into this form. Now x1 and x2, these do not need to change. So x2 is already, x1 is already 0 coefficient, so we ignore that, okay? Because 0 x1 is equal to 0. Now x2 plus 1 s1 minus 0.6 at s1 plus 1 s2 minus 0.96 s2 is equal to 3 plus 0.5. Now the tricky part is over here. The fractional part are all the fractional parts are all converted or transferred to one side, and the integer parts are all transferred into the other side. Okay, so x2 plus 1 s1 plus 1 s2, this is 3, but 3 is on the other side. When it transferred to the other side, it will become minus 3. So we get x2 plus 1 s1 plus 1 s2 minus 3 is equal to, this is minus 0.68 s1. When it get transferred to the other side, it will become 0.6 at s1 plus 0.68. Okay, this is negative. When it transferred to the other side, it becomes positive, and 0.5 is already on this side, so we we equate it. X2 plus 1 s1 plus 1 s2 minus 3 is equal to 0.68 plus 0.96 s2 plus 0.5. Now this is the Gomre cut, actually, the fractional part of it. Now we write this fractional part less than or equal to 0 form. Okay. Now when it is written into the less than or equal to 0 form, this the fractional part, the the number, it is transferred to the other side, just like we have the, what we call it, the constraint. Just like we have the constraint, we have something on the right hand side, a number. Okay, so we write it in the constraint form. Now we want to introduce a slack variable s3, because we need to write it in the standard form. Okay, so here is how we transferred into a standard form, 30196 s2. Okay, it will be added, the s3 will be added and will be equated to minus 0.5. Now this is the complete third constraint that we added. Now we introduce this to final table. Okay, the final table was, I will write it from the previous page. We had z x2 x1, and this will be s3 because we are adding this one. Here we have x1 x2 s1 s2 and s3, and it will have a right hand side. Now sorry, this is z, this is x2, this is x1, and this will be s3. Okay, now for z we have 005.09, or we can write 5.1, 2.72, and s3 was 0, and the right hand side is 126. Now for x2 we have 0, 1, 0.32, 0.04, and s3 is also 0 over here, and it is 3.5. For x1 we had 1, 0, minus 0.04, 0.136, s3 will be 0, and it will be equal to 4.5. Now this is the tricky part. here we have the x1 is equal to 0, but x2, it will also be equal to 0. The s1 is 0.68, s2 is 0.96, and s3 is 1. This, and it is equal to minus 0.5. Now using dual simplex, okay, to find integer solution. Okay, the dual simplex tells us that pick the living variable, okay, which has the negative right hand side. So S3 has the negative right hand side. Okay, so S3 will be living variable. Now to find the entering variable, we find the negative coefficients in constant row and divide the right hand side by 8. Okay, okay, now the right hand side we find the ratio. Okay, now the negative variable that we find over here is only s1, and that is in the this row, the x1 row. Okay, and the variable coefficient is minus 0.04. So we have minus 0.5 divided by minus 0.04. It will give us something around, I guess, something 12 or 13 maybe, but let's see what it gives us. 0.5 divided by 0.04. The right hand side by the negative coefficients of the constraint. We need to find the negative coefficients over here. The only negative coefficient is this one for S1. So we understand that S1 is the entering variable over here because it is only the negative. If we had like S2 also over here as negative, okay, then we will find the ratios and compare those ratios to each other, and the minimum will be taken as the entering variable. Like here in this example, okay, now here we have S1 also negative over here and S2 is also negative over here. Okay, yes, and then we divide minus 0.75 by minus 0.75 and minus 0.75 divided by plus minus 0.25. So this gives us 1 and this gives us 3. S1 gives us the minimum ratio, so S1 is the entering variable over here. Do you understand now? Now here we have only S1 as negative variable. So it is understood that S1 is the entering variable. Okay, S1 is the entering variable. Now this is the pivot column, this is the pivot row, and 0.68 is actually the key element. Okay, now should I move it further or should skip it? This is okay. Okay, now we need to make this pivot element as 1. So we will divide S3 row divided by 0.68. It will give us the new pivot row. So the new pivot row is equal to 0, 0, 0.68, 0.96, 1, and minus 0.5 divided by 0.68. So it will be equal to 0, 0, 1, and 0.96 divided by 0.68. Let me calculate it. What it gives us: 0.96 divided by 0.68. It gives us 1.41. Okay. Now 1 divided by 0.68, it gives us 1.5, and minus 0.5 divided by 0.68, it gives us 0.73. Now this is the new pivot row. Okay. Now we need to make these elements that are above equal to 0. So the new Z row is actually 0, 0, 5.1, 2.72, 0, and 126, minus the pivot element is 5.1, and the new element, new pivot row is 0, 0, 1, 1, 1.41, 1.5, and 0.73. So it will give us 0, 0, 5.1 minus 5.1 is equal to 0, 2.72 minus 5.1 into 1.41, it will give us minus 4.48, it will give us over here, and 0 minus 5.1 into 1.5, it will give us minus 7.65, and here 126 minus 5.1 multiplied by 0.73 will give us 122. This is new Z row. Now new X2 row. Using the same procedure, we get the old X2 is equal to 0, 1, 0.32, 0.04, 0, and 3.5, minus the pivot element is the here is 0.32 into 0, 0, 1, 1.41, 1.5, and 0.73. So here we get it will be 0, 1 minus 3.2 into 0 is equal to 1, 0.32 minus 0.32 is equal to 0, 0.04 minus 0.32 into 1.41. It will come 1.41 multiplied by 0.32. It is clause because when I do in calculations on calculator, then only one app works. So that is why it keeps closing like for a few seconds. Now you can see it now. Okay. So for the other one, it will become 0.32 into 1.5. Minus 0.48. It will give us 3 over here, and this is x1 row. Now we will find the new x1. Sorry, this is x2 row. This is the x2 row, not x1 row. Now we will find only the x1, new x1 row, and then the problem is solved. Now the new x1 row is equal to the old x1 row, which is 1, 0 minus 0.04, 0.136, 0, 4.5 minus the pivot column. Pivot column coefficient is 0.04, but a minus 0.04 into the new pivot row, which is 001, 001, 1.41, 1.5, 0.73. Okay, now here we get is 1 minus 1 plus 0.4 into 0 is equal to 1, 0, and 0, it is equal to 0. It will also become 0, 0.136. I need to calculate it. 0.136 minus 0.04 multiplied by 1.41, 0.2, and 0. The other one will become 0.06, and the last one is 4.5 minus into minus 0.04 multiplied by 0.73. It will become 4. This is the x1 row. Now making the tableau. Okay. Here we have z, x1, x2, s1, 2, s3, and the right hand side z, x2, x1, and here it will be s1. Now the new z that we found is 0, 0, 0, 0.48 minus 7.65, it is equal to 122. Now the new x2 row that we found is 010 minus 0.41, 010 minus 0.41, 0.48 and 3, 0.48 and 3. And x1 is actually, the new x1 that we found is here, which is 1, 0, 0, 0.2, 0.06, and 4. And the new S1, that is the new pivot row, it is equal to 001, 1.41. 1.5, 0.73. Now we see that x2 is equal to 3, x1 is equal to 4, and z is equal to 122. It is integer solution, so the problem is solved. That is how we get an integer solution. We do not need to do it further because we all got the integer solution over here. X1 is equal to 4 and x2 is equal to 3. Okay, that is how it is actually done. The problems which I sent you, you can practice it, and you can come up with some. If you find any problem, just send it to me, the area or the problem that you want me to solve it, and I will get it solved, and I will make a video or something like that, and I can then explain it to you. This is like going to be 5, and my device actually don't have charge. It is only 8% left, so I will charge it, and maybe at 4 p.m. your time. Are you available at like after an hour? Actually, the problem was, let me see the problem page. Where was I wrote it somewhere? Okay. So the problem was actually that it is a maximization problem, and these were the constraints, two constraints of it. So first of all, we need to do simplex, but they have given us the final W. This was given as the final W. So we calculated the fractional values and converted into the decimal. Okay. So the problem that we made, the mistake that we made was actually in calculations. It was not like some, and I came up with another thing that is quite normal in all these problems. So this was the final table that was given us initially. We see that here we have 3.5 and we have 4.5 over here. So as this is an integer problem, these 3.5 and 4.5 are not acceptable. We need to convert it in either into 3, this into 4, or this into 5, and this into 4 or something, but it will get converted into integers after a few iterations. So we convert this 7 by 22, 556 by 11, 30 by 11 into some decimal form, to have some, as we are converting the right hand side into decimal, so we also convert the other into decimal. So this is the final shape of the this W. Now we have 3.5 over here and 4.5 over here. So we pick x2. X2 is, it is above x1, so we pick x2 arbitrarily. We can either pick x1 or x2. It doesn't matter. Okay. So the algebraic form for this actually constraint is that we have 0 coefficient for x1, 1 for x2, 0.318 for s1, and 0.045 for s2, and the right hand side is equal to 3.5. So we write it as it is. We write x2 plus 0.3 1 at x1 s1 plus 0.045 s2 is equal to 3.5. Now we need to convert it into x plus s form. F is the fractional part of it. So here we can convert easily as 0 plus 0.318 s1 and 0 plus 0.45 s2 is equal to 3.05. Now we take all the decimals on one side and all the integers on the other side. So we take all the integers on the left hand side and all the decimals on the right hand side. Now we equated it to less than or equal to 0. We converted into this form. And then we actually add another slack variable to equate it, make it equal to 0 or equal to right hand side. And then after this, we add it to the final W. Okay. So here we add S3 as a new row and we get exactly these variables over here. For in this, x1 is 0, x2 is 0, s1 is 0.318 minus 0.318, and s2 is minus 0.045. So we add it as it is. Now we use the dual simplex method to actually have the integer solution. So the first iteration we start with. So prior to the problem that we solved earlier in the first lecture, actually, uh, we did it as right hand side divided by this, and we actually picked the minimum of it. But the more simpler way is to, this is negative and this is negative. Okay, so in the pivot row we find the negatives and divide the coefficient, the corresponding coefficients in the z row by this final row, the row that we added. So we divide 5.09 with 0.318 and we divide 2.7 to 7 divided by 0.045. So we get, hello, you want to ask something? Okay, so actually the point was that this is uh, during simplex, the dual simplex, actually, to find the entering variable, we divide the coefficients for S1 or S2 or S3, what we have like in the up till that iteration, by those variables in the final row that we added. So we divide 5.09 by this and 2.7 to divide by this, and we select the actually the minimum positive. Okay, so now, okay, so here we have the coefficient in Z row divided by the negative coefficients in the final row. So here we divide it and we get, for S1 we get 16 and for S2 we get 60. So 16 is minimum positive. So S1 is the entering variable. Okay, we enter S1 and we do all the necessary steps just like we do it in simplex. Okay, then we update it. Okay, and here we get, for in the right hand side, for x1 we get a decimal again, which is 4.57. For x2 we get 3, but for x1 we get 4.57. So it is also not acceptable. So now that x1 x2 is converted to integer, but x1 is still not converted to integer, so then again we take that respective row which has the what we call it, the decimal right hand side. Okay, now we again actually make the cut. Okay, write it into algebraic form, which is x1 plus 0.1423 s2 minus 0.1415 is equal to 4.57. Now, converting into x plus f form, we get the final value as is. Here it is given minus 0.1416 S2 minus 0.8585 S3 plus S4 is equal to minus 0.56. Now adding this into this table, the above table. This is second cut, okay? This second iteration. Now again we divide 2 by minus 0.041416 and 16 divided by 0.8585. We get the value of S2 lesser than, which is 14, and it is less than for S3, which is 18.6. So 14 is less than 18.6. So S2 is the entering variable over here. Okay. Now that S3 is the entering variable, okay, we find the new pivot row. Okay. We get this as pivot row. The new Z row we get is 0, 0, 1, 0, 14, 14, and 110. We find the new X2 row, the X1 row, and the new S1 row, and we update the table. Now this is the final table. We see that here we have the integer. Here for x2 we have integer. For x1 we also have integer. So now this problem is actually solved, and we get z is equal to 110, which is the final integer optimal value for the problem. Okay. So it was not actually one iteration problem, it was two iteration problem. I solved it in two iterations actually. I will also send you the the snaps of this problem that we solved. Okay, so you will understand it. Okay, so that was all for the cutting plan method, and now we will start the chapter 5, which is the transportation models. Okay, do you understand the cutting? Yeah, do you understand the cuts? Okay, that's good. Okay, so now we will move to the transportation problem, that is chapter 5. Okay, regarding transportation models or transportation problems, very first thing is that these problems actually have two kind of constraints. Okay, the demand constraints and the supply constraints. And these problems actually, these are based on transportation or supply of certain things from one point to another point. For example, we have two things over here. The first thing is source, and the other thing is destination. Okay, from source, something, some product or anything that is supplied to a destination point from point A to point B. Similarly, we have another source, for example C, and we have the same destination B. Okay, so now we have two sources and a single destination. But it can also be like, we have A, B, and C as destinations, and we have only one source S, and this is supplying to A, B, and C as well. Okay, and there may be multiple sources and multiple destinations. For example, we have two cities, okay, which are supplying to four cities. For example, we have some oil production facility, okay, which is in, for example, one is in the Riyadh, and the second one is in Dammam. Okay, and we have four cities that are receiving that products. For example, mm, we have here is, for example, we say Medina Munawwara, Makkah. Okay. The third one I should say is, for example, um any city like in, for example, we say something. I wrote the mom over here, so I actually, yes, Delhi. For example, the other is, for example, Lahore. Okay. So now from Riyadh to Medina, for example, these actually have like the cost function. We have cost function over here in transportation model. For example, the cost or mileage from, sorry, yes, yes, these are suppliers. These are suppliers, and these are the, the demanding cities, which the supply is actually, yeah. For example, here we have like, uh, per unit charges or kilometers. For example, here 95. We have from the Mam to Medina, for example, 50 miles or something like that. From Riyadh to Makkah, for example, 1,000 miles. And from the Mam to Makkah, for example, like 70 miles, you know, similarly to Delhi and so on. Okay. So now it makes actually a network. Okay. These are the cities. For example, I denote Riyadh by R and the Mam by D. Now we have four. This is Medina. This is Makkah. This is Delhi, and this is Lahore. So now it can provide to all the cities. Okay. Similarly, this can also provide to all the cities. Now, what we actually want to find in the transportation model is the quantities, the optimal quantities that can be supplied from source to destination, keeping the cost is minimum. So this is the objective of the transportation model. Okay. Now here, for example, we say that R, or we say that the supply S RM is the quantity that is supplied to Medina. R MK is the quantity that is supplied from Riyadh to Makkah, and R D is the quantity that is supplied from Riyadh to Delhi, and RL is the quantity that is supplied from Lahore. Now, the DM is the quantity that is supplied from Dammam to Medina, and DMK is the quantity that is supplied from Dammam to Makkah, and DD is the quantity that is supplied from Dammam to Delhi, and DL is the quantity that is supplied from Dammam to Lahore. Now, what we want to do is we want to find the exact quantity of SRM, RMK, RD, DM. We want to find these are the objective decision variables. We want to find that these decision variables in order to make the cost of the transportation is minimum. Now, I will go for like, a problem in the book. I am the Taha actually, and I will form a network, and we will try to solve it in the. We will try first to model it, and then we will try to solve it in the Torah. Okay. So now this is example 5.1-1. Okay. It is in the Taha book, chapter 5. Okay. Now here you must know that this is node and this is arc. I hope you know that this is node, the nodes and the arcs. And these arcs carry actually two kind of informations. The first information is the cost per unit. Okay. And the other is the amount shipped from one point to another. So these are the two kind of information that each arc carry in this network, in the transportation model. Okay. Now I will do an example. So example is that MG Auto has three plants. Okay, MG Autos Morris Garages actually has three plants. The first one is in Los Angeles, LA, Detroit, and New Orleans. The problem page number is 207. Yes. And it says that the capacity of these plants, LA has a capacity of 1000 cars. The Detroit plant has capacity of 1500 cars, and the New Orleans has 1200 cars capacity that it can actually supply. We can say that per month or per quarter or per year. You can say anything. You can define the duration of it, like per month or per quarter or per year. Okay. For example, we say that here it is quarterly based, like every 3 months. Okay. These are the production and the demands at two distribution centers. Now these are the supply constraints. There are two kinds of constraints in transportation models: the supply constraints and the demand constraints. These are the supply constraints, and these are related with the supply, the origins, or we can say that the supplier. Now we will talk about the demand constraints. They say that the demands at the two distribution centers for the same periods are 2300 and 1400 cars, and the mileage chart is given in table 5.1. Okay. Yes. So the chart is, this is Los Angeles, Detroit, and New Orleans, and the supply is for Denver and Miami. Okay. And from Los Angeles, these are the mileages actually. This is the distance from Los Angeles to Denver is 1000 miles. From Los Angeles to Miami is 2690. Okay. So we will deal with this distance as the cost for transportation. So we will minimize the distance covered, and we will still find a way to to satisfy maximum demands. Okay. Now, this is the capacity. The capacity for Los Angeles is 1000 cars, while for Detroit it is 1500 cars and 1200 cars for New Orleans. Now we will add these three. These three upon addition give us 3700 cars per quarter in total. Okay. Now the demand for Denver is you see over here is 2300 cars and 1400 cars for Miami. Now when we add these two, it gives us 3700 cars. It means that demand is equal to supply. So this kind of problems are called balanced models. When demand is less than or equal to supply, then the problems are called the balanced models. And when demand is greater than supply, then these are called unbalanced models. And when we have unbalanced models, we either add a dummy supply or a dummy destination, to make the demand equal to supply, depending on the situation. We will study it after we do the first problem. Okay, they say that the trucking company in charge of transporting the car charges 8 cents per mile per car. So the cost of transportation per mile per car is equal to 8 cents, or we can say that 0.08 dollars. Okay, now we will convert these mileages into the costs. Okay, so cost of car from LA to Denver is equal to 1000 into 0.08. So it will give us $80. Okay. Similarly, cost from LA to Miami is equal to 2690 multiplied by 0.08. So it will give us let me calculate it. 2690 multiplied by 0.08. It will give us $215. Okay. Now the cost from Detroit to Denver is equal to 1250 miles multiplied by the cost per mile is 0.08. So it will give us $100. Okay. Now similarly, the cost from Detroit to Miami, it will give us 1350 multiplied by 0.08. It will give us $108. Now the cost from New Orleans to Denver is equal to 1275 multiplied by 0.08. It will give us $102. Can you see it now? Okay. Now the cost from New Orleans to Miami is equal to 850 multiplied by 0.08. It will give us $68. Now we have found the cost per car from each origin to each destination. Okay, I can model the problem as, for example, here we have LA as origin, Detroit as origin, and New Orleans as origin, and we have two destinations, Denver and Miami. Okay, now the cost from LA to Denver, it is equal to $80, and from LA to Miami it is $215. Cost from Detroit to Denver is $100 per unit, and from Denver to Miami is equal to $108. From New Orleans to Denver, it is $102 and $68 for New Orleans to Miami. So this is the network now. Now let's suppose that X11 is the units transported from LA to Denver, and this is source 1, source 2, source 3, and this is destination 1 and destination 2, and X12 is equal to units transported from LA to Miami. Similarly, X21 is units transported from Detroit to Denver, and X22 is units transported from Detroit to Miami, and X31 is units transported from New Orleans to Denver, and X32 is units transported from New Orleans to Miami. Now, the objective function over here, as costs are concerned over here we have $80 of cost from LA to Denver. So it is equal to minimize Z is equal to 80 into X11 plus 215 X12 plus 100 into X21 plus 108 into X22 plus 102 into X31 plus X68 into X32. So this is the objective function that we need to minimize. This is and these are respective costs from each source to each destination. Okay, if we want to write it in general form, in general notation, we can Xij is units shipped from source I to destination J. I is equal to 1, 2, 3 up to M, and J is equal to 1, 2, 3 up to N. So there can be many sources and destination. It creates a matrix just like we did over here. This is 3 into 2 matrix. We will have a total of six, kind of decision variables: 1, 2, 3, 4, 5, and 6, because we have three sources and two destinations. So it will make 3 into 2 matrix. We will have six entities over here. Now it is subject to it is subject to constraints actually. Now the constraints over here are, as you know we discussed it, we have supply constraints and the demand constraints. First, we will go to the supply constraints. Okay. Now we say that from LA, only 1,000 cars can be supplied. So the total capacity of LA, Los Angeles, is 1,000 cars. So now LA is supplying to actually Denver and Miami both. Okay. Now the LA supplying to Denver is denoted by X11, and denote the from LA to Miami, it is denoted by X11, X12. Now the total capacity is 1,000 cars, so it must be less than or equal to 1,000. Similarly, for Detroit, we have X21 as unit transported or shipped from Detroit to Denver, and X22 unit transported from Detroit to Miami. So X21 plus X22 must be less than or equal to 1,500 cars. Similarly, for New Orleans, we have X31 plus X32 less than or equal to 1,200 cars. So these are the supply constraints. Now for the demand constraints, actually, we will go to the Miami and Denver. So we say that the total demand at Denver is 2,300 cars, and from Miami, the total demand is 1,400 cars. Now Denver receives the cars from LA, from Detroit, and New Orleans. Now we can say that X11, the cars to Denver from LA, plus X21, cars from Detroit to Denver, and X31, the cars that the Denver receives from New Orleans. So it must be actually less than or equal to 2,300 cars. Similarly, the cars that Miami receives from Los Angeles is denoted by X12, and X22 it is denoted from Detroit to Miami, and the Miami when receiving with the from the New Orleans it is denoted by X32. So it must be less than or equal to 1,400 cars. So these are the demand constraints. Now we have a complete model of it. Okay, we have objective function over here. We have the supply constraints, and we have the demand constraints. Only one thing left, that these all xij's must be greater than or equal to 0, which is non-negativity constraint, and that is must. Every source must, you know, ship something to each destination. It can either be 0 or some value, but it cannot be negative. Okay, so now this is the complete model of the problem. We can easily solve it, using Torah. Should I use Torah? Okay. 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 We have over here as three sources and two destinations. So here we say three sources and two destinations, and I will press enter. Okay, so this gives us a table. Okay, now the destinations are, I will say,